So thank you everyone for coming, and thank you Alejandro for this great talk. I think it's super important to always start with process for ethical AI. I think it's a very topical talk. Thank you so much, and I really appreciate the work that you're doing around removing the bias and ethics in AI, which is super important. Interestingly, one of the topics that people always ask me about, what are the applications for generative adversarial networks? And actually, like, balancing your data set could be one of them. So if you then want to talk about how those two worlds could sort of interact and then conjoin, then you can definitely speak to both of us about that, because I think it's one of the more interesting applications where you can actually use GANs for good. Having said that, so this is basically leading up to a paper about generative adversarial networks. But before I dive into any of that, let me just get a little bit of sense of the room. So first of all, can everyone hear me in the back? Good, awesome. Second question, who here has heard of a GAN? Okay, perfect, I like to see that. Who here has played around with one, at least there's a GAN lab in browser or trained one? Okay, much fewer people. All right, so I'll try to be fast in the first couple of slides, and then we can slow down and sort of take that in. Yeah, so about me, so I work at Mudano. I also work at Filtered, not too far from here, Pearson. I'm co-author of the book on GANs, and then I teach at a couple of universities, some companies, around all sorts of things from very introductory all the way to generative adversarial networks. So we have just seen a great example of supervised machine learning algorithms, so I don't think I need to go through that. We understand you get some data of various different formats of the machine learning algorithm, the labels, and then you sort of have the predictive model that gives you the expected label. So this is typically the framework for what's called supervised learning, right? But so we can also kind of look into the world of unsupervised learning where you don't have those labels and you're just trying to create more data out of your existing data, right? So it sounds like magic, but hopefully it is a really important exercise for us. Like going back to one of the great giants of physics, Richard Feynman, what I cannot create, I do not understand. I think it's like a helpful exercise, and that's really how GAN started, as an exercise to understanding how machine learning models work, and over time it sort of got to the state of the art what it is now, which we'll see in a second. I think why is it an exciting area? Well, it's been largely underappreciated until quite recently, and that's partially because the tech just wasn't quite there. But really what we're trying to do here is just sort of have some function, machine learnable function generate that produces some examples like MNIST, which is apparently the only data set that computer vision scientists know. Anyway, so, but what does this actually mean? So, well, most approaches use some form of maximum likelihood under the hood, right? Like really deep down theoretically. This could be either explicit, so there's things like pixel RNN, like variational autoencoders, Boltzmann machines. There's also implicit way, which is the GAN way, and we'll kind of get a bit more into that, or for those who are familiar, like Markov chains. So this is actually probability density of MNIST. So this is a different view on the only data set we know. And then we have, this is kind of what you can look at in TensorBoard. So this is another way you can just sort of try to understand your data a little bit better, but this is not very informative. But what it does tell you, though, that even if you project it with a PCA, right, it's still very difficult to understand. And this is shrunk from 784 dimensions down to 3, right? So it's still very difficult to untangle. So think about how complex the probability density function of the real data that you're trying to approximate actually is when you're dealing with images like MNIST, or even more complex, higher dimensional, higher resolution, colored images. This can get out of hand pretty quickly, right? So how do we generate in general? So this is kind of taking variational autoencoder style approach. So we start with some sort of input vector, and we have some sort of random seed, just so that we don't generate the same example every time, right? So we need some sort of inspiration, some sort of rough seed. And we have the decoder that takes this latent space into and gives us our MNIST digits, which is all we ever want. And then we're basically trying to improve this generate function, this decoder, under most circumstances, and we now get this output. So everyone with me? Yeah? Good. Okay, so what are GANs? How do they enter into this? So they're an approach to doing what we just did on the last slide, except a little bit more complicated. So let's break it down. So generative, we understand, generative model, good. Adversarial, so there's two of them. So that's the networks, so generator and the discriminator, and they compete against each other. We would get this latent noise, Z, and then we would feed that through the generator, same as a decoder in the slide earlier, and then we give that to the discriminator, which then gives us classification. Is this real or is this fake? And then the discriminator never sees like, where is this coming from? It only just gets random data and tries to figure out, oh, okay, this tends to be the fake data, this tends to be the real data. So all I ever see is like example, and I have to make that decision. So in other words, so just to summarize quickly, a generator gets an input, a vector of random numbers, and output is the data of that dimensionality that we're trying to get to. And then goal is to generate data that's fake data that's indistinguishable from the real world data set. And the discriminator kind of has the opposite problem. So it gets a sample from somewhere, either the real data set or the fake generated data set, and then it has to output the likelihood of that being real or fake. And then we have to just distinguish between the two. So, you can kind of think about it as like a iterative game between like a art gallery owner or detective and a forger and an artist, right? Who's trying to like mimic some great like Da Vinci's painting or whatever, right? And they're like, initially the forger is quite bad and sends it off to the gallery, but they're also bad because there's the first painting of Da Vinci they've seen ever, because maybe some small local gallery that never come across such a like important painting, and then so they will like get it more likely than not they'll get it right, but like not by much more. And then so over time both get better because they get like feedback from each other. So if I know that the painting that I sent was actually rejected, maybe I get some pointers. I understand, okay, I need to get better. I need to like these other things to improve, and I do a better job next time, and then the detective has a harder job, right? So that's like a neat analogy to think about it. So the key step here is that it's all iterative, right? So both the discriminator and the generator start quite bad. So if you remember from the third slide, I think, the MNIST data was quite bad in the beginning, but get better over time. And the same is true for the discriminator. So the discriminator is quite bad in the beginning, but they iteratively get better, right? And it's a balancing act of how do we ensure that one doesn't get too much ahead of the other, but there's lots of work on that. So what are the other ways to look at it? So this is the training objective. So this is kind of how it originally started, and it has underpinning in game theory. So who here is familiar with like prisoner's dilemma and the like basics of game theory? All right, perfect. So I don't have to explain this too much, but for those of you who don't know, it's basically a two-player non-cooperative game where you're trying to basically you committed a crime, for example, and then they put you and your partner into separate cells, and then you're trying to decide whether you should tell on each other or both keep silent or both tell on each other, which is the worst outcome for you, but the best outcome for, I guess, law enforcement. So this is kind of similar, right? Because you have two players and they're competing at objectives. In fact, so this is discriminator's loss function. The generator's loss function is literally the opposite, right? So they're obviously competing against each other and trying to get to the best outcome overall, which is how they improve over time and they get more and more realistic samples, right? So if we break this down, I'll go into it a little bit. So basically, this is the part where we're trying to take the generated samples, right? So we have the latent space Z from which we sample. We feed that through the generator function, and then we feed that to the discriminator to tell. Like, this is the part that punishes the discriminator if it gets a generated sample wrong, and this is the part that punishes the discriminator if it gets the correct the real data labeled as fake. So there's a slight improvement on this, which is the non-saturating version, which was also proposed in the original paper. I kind of included more for completeness because nowadays it's kind of surpassed mostly. I mean, there's still a little bit of an argument about that. But by the Wasserstein GAN, which we'll see in a second. Well, so let's come back a little bit to motivate all this hard work. So why is this an interesting problem? Again, largely unexplored. A lot of the applications are just people are just making them up as we go. Like there's literally this, it's such a new space that it's very difficult and non-trivial oftentimes to come up with all the use cases. Some people are using it for medical research, protein folding, game simulation, like generating new levels for a computer game, all sorts of things. I will not go into those in the moment, but if you're curious, we can talk afterwards. And what you're looking at here, this has been the state of the art until about, I think, 2016. So this was the best we could do in generative modeling until 2016, right? And then earlier this year at ICLR in Montreal, I believe, or somewhere in Canada, came along this paper, which was about progressive growing adversarial networks. And all of these full HD 1024 by 1024 images of celebrities. All of these are fake. They're synthetic data sets, synthetic data points that have been generated at an amazing level of detail and precision, right? One of the great things about GANs is that unlike VAEs, which is where this is coming from, you can see that the facial features are quite clearly distinguishable, but the background is super blurry because it's VAEs have minimized kind of the overall loss, and they have a single loss function. So they don't actually decide, they don't want to commit to any particular instance, so they can't decide on the background. Whereas GANs, they can kind of commit much more easily to anything even, I mean, the backgrounds are still a little bit difficult, but you can at least see that the edge facial features are very good. And actually the reason why it might not look as impressive is just because of the GIF quality, but I couldn't make a bigger one. Anyway, so what is GAN actually doing? So in this particular instance, we're using what's called the Wasserstein GAN. This is also from the same paper. It's just kind of going through a couple of bedroom examples and sort of iterating through the latent space Z, just kind of going through and trying to generate adjacent examples. So what Wasserstein GAN is doing, and you have like a simplified loss function down there, it's still kind of similar. They're still competitive, but the main thing that we're now trying to do is we're trying to take the real data distribution and the generated one, and trying to figure out, okay, if I imagine this as a mold, right, like a piece of, like a mold of sand or something, how much work would it take to transport all of that probability mass so that it looks exactly the same as the real one for the generated distribution? Does that make sense? So imagine like imagine you took the probability distribution and plotted the likelihood of all the images that you had, right? And that defines some probability distribution function, right? Then you look at a whole bunch of initial seed values. What would that look like? What would that equivalent distribution look like if you just wanted the synthetic data, right? And then you sort of compare the distribution and look at how much work would it take to mold the generated one into the real one. Yeah? Okay. So this is the underlying sort of loss function and game setup that this particular paper is using. And the other thing is the manifold assumption. So it's just like, when you think about it, it kind of makes sense, but it's worth making that explicit. So what we're saying here is that for each sort of set of real data points, you can construct some sort of latent space vector that would output that that example. So you're basically taking a super high dimensional space and you're trying to sort of twist it or contort it in a particular way so that the two distributions are exactly the same, the two manifolds are the same. So that's kind of where the Wasserstein and the sort of the Wasserstein loss and the probability density transformation comes in, right? So you're basically trying to take what you would get by the untrained generator, right? That defines some probability distribution, some manifold, and contort it so that it gives the same manifold as the real distribution, right? And that's kind of a neat analogy to think about it. It's like, think about it as like some archipelago and some bunch of islands, right? Initially you'd start out all over the place, right? Because it's kind of like untrained generator doesn't really know what data is more likely to be real than others, right? So these are these horrible, ugly examples. And then you're trying to contort it so that it matches this weird space, which we probably never get fully observe, but matches those islands, which are kind of realistic looking, and we're trying to push the contortion so that it gives us the output that we want. This is such a great visualization, and it's used by the original papers by the authors already, but I think it's just so helpful. So this is the Wasserstein loss. It has this extra term. I wouldn't worry about it. It's just basically gradient penalty, but not worry about that too much. But think about the two think about it almost as if you have some sort of surfer, which is like your current generated point, and you have your like wavy C, which is your loss function, right? Like you have all sorts of or like your probability density function, more like, and then you're trying to adjust your loss function so that you push your generated example towards the good equilibria, right? Towards the good sort of islands where the masses, where the two manifolds overlap, right? So what the generator comes up with an example, the discriminator then trying to adjust the loss space so that it pushes the generation closer to the land. Yeah? Make sense? Some confusion. Okay, I don't know if we have, hopefully it'll become clear. So the neat innovation of this paper is that it progressively grows both networks. So we start out, like both generator and discriminator typically would be some neural network. They're not always, but typically. So you would start out, if you start out in 1024 by 1024, the space is massively complex and massively spiky, right? So it's very difficult to navigate that space. It's very easy to get stuck in local equilibria, right? That sort of thing. So what they do instead is that they scale back and they put like much more easy to navigate space, which is much lower dimensional. So they actually start in 4x4. I think this animation is slightly different, but the actual implementation starts 4x4 blocks. And then both algorithms get more confident, not only do they iteratively train them, but they iteratively grow the capacity of the two networks as well, right? So they progressively get more sophisticated. So we have a 4x4 space, very low resolution image. I don't know, is this not going? Oh yeah, it is. Okay, and as we push the surfer towards the sea, we kind of increase the capacity, and sort of this space behind the surfer gets horribly deformed, but that doesn't show that. But we also we can increase the speed as we get more confident with our training, right? And obviously the nice side effect is that we get much higher resolution images. Obviously just doing that would kind of when you introduce the next layer, that would introduce a massive shock to the system. So what we do in the beginning is we just take a standard 4x4 and we upscale it with some like bicubic or some like algorithmic upscaling that's usually not trained or has only very few parameters. And then we smoothly merge the fully trained 8x8 and the upscaled 4x4 to 8x8 and sort of have some parameter alpha that like switches over time from one to the other so that we don't shock the system, if that makes sense. So we sort of like smoothly try to introduce slowly the higher capacity network into the training process. So variation has been one of the areas where GANs have typically had some trouble. So this image actually is from was been labeled big GAN, which is probably the state of the art in conditional generation. But you can see that even for an alternative model which doesn't use this progressively growing, some of these images are absolutely astounding. And it just kind of does like smooth latent space interpolation between like a couple of vectors just to show you what do adjacent pictures look like. But you can get, even with a different model, you can get quite interesting pictures. But going back to our progressive GAN, so what typically happens is you get something called mode collapse. So all the initialization of the initialization of the z space of the latent vector get allocated to like converge into one area, which the discriminator cannot tell from real from fake because it kind of already decided that looks real enough. So what we try to do instead is we try to force them apart in the early part of the training process by just introducing a slightly different training regimen. So you see like the mode collapse, everything converges to one point, so we try to spread it out quite early and then map it out onto the manifold. So the first step that we do is we obviously do batch discrimination. So we don't just do like a single example, but we have the discriminator faced with the whole batch. That's, everyone kind of does that. The problem is the discriminator doesn't still know which batch does it come from. So what we do instead is we add an extra feature map, which makes it easier. So here we have 3 images, and then we map them, and we average over each of the dimensions. So we first, do the standard deviation over the different images to get a single feature space of height, width, and channel. And then we reduce that to just 2D, and then we reduce that to ultimately a single scalar value that then gets that basically represents the diversity of that sample. So if you think about real data, it will always have some reasonably high standard deviation, some reasonably high variance, and then we just append that as a feature map into one of the last layers of the discriminator. So that way the discriminator has a strongly predictive feature, which it knows, like this is the variance, and very early on the discriminator figures out, oh look, like if the variance is low, there's mode collapse, so it's very easy for it to tell which samples are fake, therefore the generator has to get better. Yeah? Makes sense. So what has all this hardware gotten us? That's a fair question. Let's take a look. And one thing so this is kind of showing the progressive growing. And one neat thing that I love about this clip is that they really show like how iteratively you get from lower and lower resolution to in a quite predictable, stable way to a high quality, high resolution. I'll play it again. High resolution, high quality images that sort of converge into something that looks pretty realistic, whereas if you start with a fixed resolution, it kind of oscillates all over the place. And you can see both the increasing resolution and the increasing quality. So it's kind of good. Obviously, it takes quite a while, but the researchers are from NVIDIA, so I'm sure they don't have a problem with GPU computes. Anyway, so in context. So this paper introduced a whole bunch of other innovations that I won't talk about, some of which are quite important. Still, some of which have kind of been surpassed, like slice-Wasserstein distance. Doesn't look like it will probably be the prominent way of evaluating these metrics. So there's other ways that have gotten similar results, like spectral normalization GAN or big GAN. There's already a couple of extensions using this technique proposed. There's already a couple of practitioners using these techniques. It's one of the first models to be put on the TensorFlow Hub, which is a cool repository of pre-trained models. So the amount of GAN papers is growing like crazy. I think there's over 1,000 now. I think it's a little bit outdated, but it's growing literally exponentially. I don't think we'll go through the code. I don't think we have time. Some references. And so as I said, I'm writing the book. So if you want to buy that, there's a bit.ly link. we're trying to write it almost at a level as if you're willing to do a lot of Googling and you've read like some introductory book like François Chollet's Introduction to Deep Learning, then you can probably, like with a lot of Googling, you can probably read our book, hopefully. And also at Mudano, we're hiring for, I'm in the R&D team, but we're hiring for client-facing data scientists. So if you're interested, you can talk to me, definitely. And yeah, that's it.
Hi, I'm Pedro. I'm from Zag, a fraud detection company. So when you're working with GANs and you're inserting the noise into the images, that when the generator is doing that, what would be a similar step, but for situations, for example, like Alejandro was talking about, where the features are age and gender, and so if you put some noise, you can get another realistic person, right? You change the gender to another gender, change the age to another age. It's fake or true, right? It's hard to tell in a situation like that. How would you go about doing a GAN in a situation where even after applying the noise, you cannot really tell if it's a fake or not fake example?
Right, and so I almost don't understand like your challenge. So I understand, okay, so in tabular data, right, I guess that's part of your challenge. So in tabular data, it is a little bit different, obviously, because GANs have been applied in those situations as well, but they, obviously, you need to really think about how do you set up the two networks, because it's obviously, like, if you have categorical features, that's one of the reasons categorical features require a bit of like slum hacks, so you can fully propagate, like backpropagate the error in both networks. So that's one of the reasons why NLP GANs have typically required a lot of tinkering before they can work. In tabular data, I think it's slightly better, just because the dimensionality of that is lower typically. So you can do that. There's papers where the people have like managed to, for example, like sort of take data sets from different hospitals and then merge them into like that have different data gathering processes, and sort of project that into a shared space so it can train on the data set across all hospitals.
Is that one of the papers that you cite there?
No, I think it's called GAN, Generative Adversarial Imputation Network.
Maybe I can.
Yeah, or you can talk. Yeah. But I think that was like, I had a second point, but I forgot it. Anyway.
Was it one at the back? Or was it just someone you like? No? Yes.
Thank you. Stephen Simmons from Open. Do you have any examples of where this is used in like real industrial processes or real life rather than academic curiosity?
Right.
Ideally, something not involving images.
Right. Okay. So. Okay, I'll start with an sort of image example just because it's easier. Though actually, I mean, there's all sorts of variety of images. So some of my friends from a like healthcare startup, they have used this exact technique, in fact, to generate sort of CT scan and mammograms and generate synthetic data sets of that, which is a potentially interesting application, either for data augmentation, class imbalance, even like sort of like privacy, right? Because if it's a synthetic example, it doesn't actually belong to anyone. There's like, you know, that's also kind of imagery, but like very different type of images, right? Obviously, there have been people who've been like applied this to super resolution and compression. Yeah, I mean, I think there's a couple of interesting examples of like tabular data. So GAN, there was also one research paper funded by the Office for Naval Statistics that basically, yeah, managed to generate like synthetic tabular data, as well as this projection into shared space that I talked about earlier in the previous answer. So there's like all sorts of applications. I think One area where I don't think it's working super well right now is probably natural language processing. That tends to be difficult. There have been papers that tried it with some high-profile authors that have generally achieved like interesting results, but like they haven't beaten the state of the art, I wouldn't say.
You said just one in the back, and then Alejandro is next.
So I'm Michelle, I'm from Bartlett at UCL. So what if instead of getting the generator to fit the distribution of the real data we improve the discriminators, so we make the detective better at detecting fakes. Has that been coming up in research at all?
So, all right, so you're kind of interested in almost like semi-supervised learning kind of setup.
Yeah, so
Right.
we can, what if we make the discriminator better at detecting fakes, rather than getting the generator to fit the distribution of the real data better?
Right. So just so I understand the question, so there's some like whole bunch of research in like semi-supervised learning that have used the GAN to basically like, in essence, like in the loop data augmentation. So you get a better classification model. So typically you care more about the generator, but there have been instances where people have like said, I actually want a better discriminative or classification model. Is that, okay, cool. Yeah, so semi-supervised learning has been like, in fact there's a chapter on it in our book. Lots of people have tried it, typically most successful in visual images just because that's where the research has been going for the longest. Also remember, this is all at the very most 4-year-old stuff, right? Some of the applications, NLP, music, all sorts of like exotic data types are much later, right? And therefore much newer. So semi-supervised learning has been successfully applied across a number of visual tasks. There are interesting debates about like the realistic evaluation of semi-supervised learning. Because it gets tricky, right? Because you are still only exhausting one data set, but typically people beat in fairly realistic setups what they would have gotten without the GAN in the loop. So they definitely provides a noticeable improvement, but you just have to be extra careful about how much that is.
I'm actually quite curious of, so what are the properties that currently, or the limitations that currently GANs have that make them not able to perform as well in text? And just wondering whether it's the recurrent properties of it. If it's that, is there use cases of replicating like financial data and whatnot?
Right. Yeah, good question. So I think, so basically that is the sort of like 10-second summary is the recurrent nature of the text that makes it really difficult. Typically, the papers where GANs for an NLP have performed better have been very like weird formulation. Well, I wouldn't say weird. Non-standard formulations of the NLP task, right? So like fill in the gap, right? Like you like take a text and the way you generate your data set is you just like mark out one word and then predict that. So it's highly constrained, right? So the GAN can actually do quite okay and generate like realistic, like maybe blur out like the middle 3 words and see like, and it usually comes up with a reasonable prediction, but that's not it's not a very standard NLP task. So those tended to be more successful. So I think that intuition is roughly correct, or to the best of our knowledge. You had a second question.
Or the financial data.
Financial data, right. Financial data, yes. So I have seen some evidence of that. I think mostly in data augmentation on semi-supervised learning settings, because no one really cares about generating time series for the fun of it. Some people might, I don't know. So there is some evidence that is happening. Obviously, if you would know, though, I wouldn't assume that you would like yell about it everywhere, right? You'd probably keep it and make all of the money, right? So I think I have seen like some evidence that is happening, but obviously the paper's either not very specific, or when you just talk to people informally, they will tell you like, oh yeah, I've looked at that, but they wouldn't actually like tell you all of what they're doing.
Can we talk one more? Yeah, fourth row.
Prasad, just on my own. Just a quick question. When you say generative and discriminative networks, just to start with, is it like classification being easier when it comes to neural networks versus generation of something is entirely a different ballgame? We are totally going in different directions. Because I mean, most of the examples that you see on AI are actually trying to classify into something.
Right.
As opposed to you're starting with absolute nothing.
Yeah.
And trying to create something and try to identify or verify yourself that whatever I've generated is actually what I can classify. I'm not sure if I made my question.
I don't quite understand the question, sorry.
Okay, so the way I see it as you have got two networks. One is trying to generate something and the other one is trying to verify whether the generated one matches something or not.
Yeah.
Most of the examples are actually trying to classify into one or other types on which the network is already trained.
Right.
So are we going a step ahead and trying to say that, here I've got a noise, completely random information. I'm trying to create something.
Right.
Because I've got just one direction. I don't have any other direction to come back from, because I'm trying to mimic something here.
Right.
Is that the right way of...
Yeah, so I mean, I think it's so I guess what you're saying is like so far most of the progress in the like recent years in AI has been supervised well by you. I have some data and I have some label and we just gotten better at classification. Yeah, I think that's correct. And I think GANs are probably one of the first, I would say in fact GANs are the first sort of general purpose with an asterisk with like some potential qualifications framework for generating new data, which also means that it's unsupervised, right? So you don't need those expensive and hard to get labels. You just like generate data that on like pretty much all the observed variables looks exactly and distributions looks exactly like the real thing. In fact, there was some work in astrophysics where they had tried to generate, I think, some like light scattering using GANs, and they like. And I think in network theory as well, and they like always are so surprised when they like look actually it matches on across all the like different ways to slice the data. It actually exactly mirrors if you train it well, exactly mirrors the underlying original data set. So typically previously had to fine tune every generative algorithm to like match about the variables and the dimension that you cared about, which now is sort of for free if the GAN is fully trained and fully converged. But so is that a step ahead? I mean, I think that's like an open debate right now. I personally, I'm very excited by the progress that lots of the researchers and practitioners are making. I think that's awesome. I do kind of think that is kind of the way forward because labels are the limiting factor quite frequently. But obviously some people might disagree. I think it is kind of the next step because like supervised learning, a lot of it has been largely solved, and I don't think it's unfair to say that the progress across a lot of the classification tasks is kind of plateaued. So this is like the new exciting area where like that's the frontier, it's the brave new world, right? So hopefully with none of the negative connotations, but we'll see. So I think it is kind of going ahead. Like other people might argue that reinforcement learning is the way to go. I think GANs are interesting in their own right. So
does that mean that crime prevention versus hackers?
Sorry, crime
prevention versus hackers. Is that something like that? I mean, they are just constantly fighting against each other. Are we giving a tool to hackers that
are you?
Weaponized GANs.
Yeah, well, I mean, so actually, I think I have seen some work in cybersecurity with GANs. There's a couple of papers, some of them coming from like the Czech Technical University. Again, like with any technology, it's a tool. I think it's important to talk about it first and foremost so that people know. Right, can it be misused? Yes, probably. In fact, I think if you look at it, you could already come up with a couple. I think the first important thing is that people need to know about it. Right, because without knowing about it and then democratizing it, like you can easily get caught off guard. And progress is like you can't reverse progress. I don't think so. I think it's definitely an exciting area of research. I think there's a lot of like work to make sure that the AI is being put for good. Right, So,
Very good. Thank you.